So far we discussed about the behavior of concrete in compression, and now it is time to analyze the behavior of concrete in tension. It should be borne in mind that concrete is very weak in tension. Unlike in compression, concrete is very weak in tension. The tensile strength of concrete is only about 7 to 15% of the compressive strength of concrete. The strain at which the concrete fails is very small. It is of the range of 0.0001 to 0.0002. This is extremely small, and hence the line joining the origin and the fracture point is generally assumed to be a straight line. The strain value is extremely small compared to the failure strain in case of compression. Now let us study the behavior of concrete in flexure. By flexure we mean the concrete specimen is subjected to bending. This behavior of concrete is very important and shall be used in the design of flexural members such as beams and slabs. You observe these figures very carefully. A concrete beam is taken for flexure tests, and as the concrete bends, you observe that the top fibers come together and the bottom fibers tend to move away. Hence the top fibers are subjected to compressive stress while the bottom fibers are subjected to tensile stress. Since the tensile strength of concrete is very small, it is expected that the extreme fiber at the bottom, where the tensile stress is large, shall fracture first and the crack propagates upward. Hence it is understood that the plain concrete is absolutely ineffective where the tensile stresses develop and cracking of concrete occurs first here. It is because of this reason that we must use steel bars or steel reinforcements in the tension zone of flexural members. In the tension zone of flexural members, as you see in this figure, on the tension side you embed steel reinforcements in order to compensate for the concrete's incapacity to resist tension. Hence it is because of this reason that we embed steel in structural members made up of concrete, and we call them reinforced concrete structures or RCC structures. Further, the reinforcing steel imparts ductility to the structural member. How? A properly reinforced beam, if it is expected to fail in tension, then with the presence of steel, instead of abrupt fracture, it results in yielding of steel in the tension zone. This results in large scale deflections in the structure, which gives ample warning to the user before the impending collapse. Reinforcing steel or reinforcing bars, or in short rebars. These can be classified into two: plain mild steel bars or MS bars and HYSD bars or high yield strength deformed bars. Physically they can be distinguished from this figure. The first one represents the MS bars, where the surface is quite plain, there are no deformations, but the HYSD bars have a deformed surface. The plain mild steel bars are generally of the grade Fe 250. By 250 we mean the yield strength of that grade of steel is 250 megapascal. But HYSD bars are available in two grades, Fe 415 and Fe 500. The yield strength representing 415 megapascal and 500 megapascal respectively. Now let us understand the features of the two kinds of bars from the stress strain diagram. Given here is the stress strain diagram. You observe the Fe 250 bar or the plain mild steel bar. is found to have a well defined yield point, and the elongation of this material is very large. This material is very ductile because of very high value of failure strain. But you observe the case of Fe415 and Fe500 bars, where there is no well defined yield value. Just as we described the characteristic strength of concrete, we should describe the characteristic strength of reinforcing steel. For mild bars or Fe250 bars, the characteristic strength is taken as the yield strength of steel. And for HYSD bars or Fe415 or Fe500 bars, the characteristic strength of reinforcing steel is taken as 0.2% proof stress. So we should know what is 0.2% proof stress. This is measured as shown in this figure. The stress strain diagram of Fe415 or Fe500 grade steel is shown here, and corresponding to 0.2% strain or 0.002 strain value, you draw a line parallel to the initial portion of the stress strain diagram, which intersects at a point on the stress strain graph, and the y coordinate value or the stress value which corresponds to this point is the 0.2% proof stress.